We're going to be talking today about hybrid grounding, what it is and when, why you should use it. We're going to start off with saying that we're going to have a question and answer session at the end. If you have any questions, please feel free to, on the questions tab, write your question. We have my counterpart Stu. He's going to be looking at your questions. We're going to either answer at the end or answer during the session via written response. So, and if we don't happen to get to your response, we'll go ahead and email you the response. So this is the second installment of our webinar series. About me, my name is Chris Small. I'm a Post Glover application engineer, regional sales manager for the last 12 years at Post Glover. I graduated with an electrical engineering degree from Ohio State forever and a day ago, to be honest. I'm sure many of you out there are in the same boat, hopefully. Of course, I am getting older, so. But that's enough about me. Let's talk about today's topics. One thing I will mention is that we're going to be getting into a bit of detail today, but if you really want to understand the totality of how to do a hybrid high resistance ground, how to set the relay settings, all kinds of details, this is kind of light on, not super heavy on details. So there are some references at the end of the presentation that you can refer to if you want to get heavy on details, because we only have 45 minutes versus a couple hours. So anyway, today's topics. We're going to start with the resistance grounding review. Just for those of you who don't know the topic or what that is, we're just a very quick review. Then we're going to introduce the hybrid high resistance ground, which I'm assuming more of you haven't had introduction to. Why use hybrid high resistance ground? Design considerations, some applications, and then an economic analysis. So that's kind of the direction we're going to be taking today. So we start off with high resistance ground. This diagram would represent either a high resistance ground or a low resistance ground. Essentially, your Y point source, you have a resistor in series between neutral and ground. If you were to have a delta system, you could derive a neutral here, but it's a neutral derived resistor off of the ground point. So it's neutral to ground, neutral resistor ground. That's how it works. So the high resistance ground, IEEE talks about how you have a high resistance ground when the allowed ground fault lead through currents is 10 amps or less. Now some of you have used a continuous HRG system that's more than 10 amps. It's kind of a loose definition, to be honest with you, but IEEE defines it that way because they have done studies and testing to determine that 10 amps or less, there is no damage to your system. I don't believe that testing was done above 10 amps. So just an FYI for you guys. Allows faulted circuit to continue to operate. That's one of the benefits of high resistance ground. It's a reason why it's called high resistance ground is it's a higher ohmage, less current because it's inversely proportional to those things. So the highlights of it: allows faulted circuit to continue to operate, limits a large percentage of your arc flash potential, and then it significantly decreases shock potential due to stray ground currents. This is going to be one of the components of a hybrid grounding system, so I wanted to introduce it to you if you haven't already seen it. We move on to a low resistance ground system. Once again, exactly the same way you hook this thing up, it's just the resistance has changed. Now you're a lower resistance comparatively. IEEE defines it, kind of gives you some example for industrial applications: 100 amp lead through current, 200 amp lead through current, 400 amp. Those are the common industrial values for lead through current. And just in case we're not clear, lead through current just means the allowed ground fault current that the resistor lets go through. We have this in Ohm's law: V equals IR, voltage equals current times resistance. Your resistance and current are inversely proportional. So the higher you go up with resistance, the lower your current's going to be, and vice versa. So the advantages of a low resistance ground system are relay coordination, excessive damage to equipment. One of the ways we actually do relay coordination, and the reason why it actually works, if you have a solid ground system, let's say, you're going to have potentially thousands of amps of ground fault current. If you have a resistance grounding system, you get to define that value, right? So let's say you have 400 amps of let through current. So when you get a fault, the ground fault, you're getting 400 amps versus a few thousand. Well, if you have a few thousand, you're probably going to want to trip as fast as possible because that's going to cause excessive damage to your system, and you want to trip as fast as possible. That means that your coordination time is hampered. If you're high enough, basically from a relay perspective, you need to trade off between very fast tripping or instantaneous tripping and risking some relay issues, some coordination issues, or you accept more damage. So whichever one you accept, usually a low resistance ground system will, because of the lower current, will allow you more time and therefore will help with that coordination while reducing the amount of damage. If you get below your damage curve, you can eliminate your damage, but sometimes you can't avoid that, but relatively your damage is going to be much lower. Another disadvantage is of a lower resistance ground system is you must trip essentially. So it's similar to a solid ground system that you must trip, whereas as a high resistance ground system you don't have to. Now once again, this is the hybrid grounding system. All it means is a combination of the two, of the low resistance ground and high resistance ground. So that's why I want to go over these two. Which is what I just mentioned here. This is a picture of one of our hybrid resistance grounding systems. This is a high resistance ground resistor. This is a low resistance ground. Just examples of such. You have a transformer, CTs, surge suppression, etc. We'll go over the components of it, but it's just to show you an example. Also an example of our display. You typically would need for hybrid high resistance grounding would need differential protection. It's probably the cleanest and best way to provide the protection you need. We'll go into that detail more later as well. So the general idea of it is you're going to have a low resistance ground system for the vast majority of your faults. Okay. However, for the faults that are located in the generator, essentially in the generator, area, stator faults, etc., you're going to be high resistance grounded, and we'll kind of go into what that looks like. And so here's an example of a drawing. You have, this is a single generator. You have your generator with some relay, we'll go into in a minute, but you basically have paralleled a low resistance ground resistor, and like I mentioned before, 400 amps is a very common current rating, and 10 seconds is a very common time rating. Then high resistance ground is 10 amps here. So those are in parallel. Well, like you saw before, you can put those into a single enclosure. And the stuff that I mentioned before is included potentially: vacuum switch, arrestor, filter, and resistors. This is very important. This is very common for a single generator application. So this is a multiple generator example. One thing I will mention, I didn't actually show it in one of my slides, but you can actually do the hybrid system we just showed you with the parallel resistors. You can do those in this type of a situation where you have parallel gens. You can actually do that and just repeat it over and over again. So you have an LRG and an HRG per generator essentially. I didn't show that, not that it's not a viable option. It is. It's definitely a more expensive option. This is a viable option for parallel gens. I think, in my opinion, is more practical. So this is why I showed this one. But you essentially have the low resistance ground resistor hanging off of your bus right here, off of 3 wires. You're going to be deriving the neutral with what here is a zigzag transformer. So you have a neutral here. You have your resistance grounded off the low resistance ground right here. Per generator, you have a high resistance ground, typically resistor only package. And what happens here is you essentially trip off your main breaker if you have a fault inside your generator. If you do not, the ground fault current here is all active. So because of all available ground fault points, essentially your total overall current is 440 amps. So you'd be acting as a low resistance ground system with 440 amps for almost all scenarios, except for internal to the generator, where you would figure this out based off of the relaying that we'll talk about in a second, and you would trip your breaker here. So let's talk about the relays and how that works. I'm not going to pretend that there's only one way to do this. There are a few different ways to do this. We're going to go over a popular way to do this. Like I said, just kind of introducing the topic to you. I don't want to, like I said, there's different various options here. So we have a generator here. This is our single generator example. We have our overcurrent protection here and our differential going into a master switch. We have typically a fast speed switch here with our LRG, and then we have overvoltage protection at the HRG. Basically what happens is if you pick up when you relays, this switch is going to tell simultaneously both your main generator breaker and your, basically I would call, I guess, a resistor breaker, typically a vacuum switch here, to go at the same time and trip offline. So you're isolated without the low resistance ground. So basically, I guess you could say you're isolating low resistance ground, therefore you're operating without it. And so you just have basically a 10 amp resistor wind down. So I'm showing you what it is at this point. Obviously we'll talk about why here in a second. Let's go over some of the, just if you haven't seen this before, differential relaying, just to give you an example. Essentially, you're talking about current inputs or current detections at both sides of your protection zone, usually each side of your generator. Essentially, if you have a fault outside, right, which is shown here, the current here is you'll have a fault here. It will change the overall current potentially, but it will maintain this continuity inside the generator. So you won't actually have any reason to trip based off of this example. If you were to have a fault internal to this zone right here, this is where you would see a differential between your two different CTs. At that point, that's what differential relaying would do. It would trip based off of that. So we're isolating faults internal to the generator for basically tripping and tripping at LRG. Just to give you some more definitions quickly, most of you are probably familiar with this. This is your overtime, neutral time overcurrent. Essentially, you're based off of a certain amount of time. You have overcurrent, you're going to be tripping. Master trip relay is based on whatever inputs you receive. This is going to tell your different breakers to trip, however you program it. This situation would be basically the same time. You want this one to trip at the same time or just before this opens up as well. Then you have your neutral over voltage relay right here on the HRG typically. So this is a typical setup of relays. Once again, we're not going to go into the settings. That can get more complicated, but you can refer to the references at the end. So poll question number 1. Let's get some input from you guys as we move forward. I'll give you about 15 seconds so we can share some results, and then we can move forward. All right, let's move forward.
Just as a side note, the vast majority of our listeners today, basically 75%, have not designed or implemented hybrid grounding previously.
Okay, thanks. Just off of that, before we move forward, there's some history. Essentially, this was really a big topic about 15 years ago. Not that it's not a big topic now, but my point is that this was a buzz in the industry. IEEE was writing a lot of papers. There are a lot of IEEE papers on it, et cetera, based off of some issues at some different plants and some unexpected results. The point is that in my personal experience, I've seen the popularity of this stuff grow, but it's still just based off of, I think, knowledge and familiarity. So take that in mind. I think it's similar to high resistance ground in the sense that as more people understand it and they apply it to their applications, I think it'll get more popular as well. So let's go to the why. That's pretty important. We talked kind of about the what it is. Let's go to the why. To do that, let's back up just one step. Let's talk about the Green Book, IEEE Green Book, and medium voltage generators. So this just to be specific, this is really a medium voltage generator application. We're not really talking about many other, I can't think of another application to use this on. So if you don't deal with medium voltage generators, you're probably not going to see this very often. But generally speaking, and to start, IEEE recommends that if you have a medium voltage generator, you want to impedance ground it, okay? That would mean reactance ground, that would mean resistance ground. We're not going to, I've mentioned before reactance grounding, and we did the entire presentation on it. If you're interested in that topic, please refer back to that. One note I will make from that presentation is about 95% of all industrial applications are going to use resistors. So we're going to kind of skip the reactance part, assume you're using a resistor, and say that basically you're starting off with a resistor for medium voltage generators, okay? And so the reason why that is because at the end of the day, you have a potential for a ground fault being higher than the three-phase short circuit current that the generator is braced for. And that's based off of your variation of positive sequence reactances versus zero sequence reactances. We don't need to get into those details, but the bottom line is you need to be braced correctly. Medium voltage generators are not necessarily going to be braced correctly on a solid ground system. Therefore, IEEE recommends users use a resistor. So we start off at that point. We already have a low resistance ground system for our generator. The problem is, and I mentioned it already, there was, I think the first victim of this, at least the first published victim that we know of, was a fairly large pulp paper plant. We don't need to go into details of who it is, but basically they had a low resistance ground system on cogen systems, very popular design to have, obviously generators as well. But they had a fault. It turned out to be inside the generator, and the damage that occurred just was alarming to them. It was a lot more than they were expecting, based off of usually what happens in a low resistance ground system. So the reason is because this is your system, this is your generator current, and so your system's going to trip here when it sees this elevated current, okay? And so your generator is no longer, your system is no longer active in one sense because you're trying to shut down, but you're not shut down yet. You're still winding down, and what you're doing is you're winding down with that fault. So you have a time where that wind down period is going to actually create more damage. In fact, there was a paper done, and it was a study done that was basically showed that the majority of the damage that was created in that type of fault was from the generator itself. So what the point is that you're actually creating more damage after you trip than before. So there was a significant amount of damage. That is what actually can happen when you have internal faults to your generator. You don't necessarily have, if this was a solid ground system, you might, you probably need a new generator. If you have a low resistance ground system, you're going to have some serious rework probably, just because of this extra time that this is winding down. Okay, so yeah, you basically need to account for this, and that's why you're not fully protected. Even though the vast majority of situations you're protected with the low resistance ground system, you're not fully protected on the medium voltage generator unless you would have a hybrid grounding system. So, like I mentioned before, for generators, you have really hybrid grounding assumes you cannot use high resistance grounding. I mean, I think that for most of the research I've done and most of the application I've seen, usually at the 15 kV level, one of the reasons for that, I believe, is because now, especially nowadays, 5 kV is more likely that you could use high resistance ground by itself. You don't, if you have a combination of high resistance ground and low resistance ground, and you're basically adapting the benefits of high resistance ground, which are lack of damage to your equipment over an extended period of time, continuous period of time. If you can just use high resistance by itself, then why would you use hybrid essentially? So that's the point. So if you were to look at your 5 kV system and you want to apply hybrid, I would recommend you would first figure out if you could use high resistance ground by itself. And for that to happen, you need to do a capacitive charge current analysis. We're not going to go in detail on that, what that is. We've done it before on different previous. Basically, it's the amount of current that your system's capacitance produces on a ground fault, and it competes with the high resistance ground system. Bottom line is you don't want to overvoltage your system, so you want to make sure that's low enough to use high resistance ground. Once again, if you have a question about that, feel free to ask. We'll take it. But we've also addressed that before in a previous presentation. 15 kV, that is less likely. You're not going to probably use high resistance ground in the traditional sense. I mean, you could definitely use it for, so two reasons. One, the capacitive charge current is too high. That's if you're looking for continuous operation. You know, it's too high to operate a high resistance ground system. And usually at the medium voltage of 15 kV, you're going to need higher ground fault current to be able to see your faults. Your relays are going to need more current to see your faults throughout the system. So it's less likely that you're able, although I will tell you that we definitely see high resistance ground systems being used at 15 kV for generator protection. That is for sure happens all the time. So it can be done, but just keep in mind what the parameters are. And, you know, also economic. I guess I'll talk more about this later, but basically it comes down to, is it worth it to spend extra money on the additional resistors to protect your system from essentially generator faults? And so that kind of obviously is application specific. We'll try to go into that in more detail, but that is kind of a bit of the why. In terms of design considerations, one thing I will mention is that a lot of these design considerations are for your single generator with a low resistance ground, high resistance ground in parallel. You're essentially tripping offline a 400 amp resistor or whatever the resistor is going to be, but a larger resistor, and your currents are changing, and you're going to develop some transient overvoltage or transient voltages essentially, and you can have some issues with overvoltages. In our example with the medium voltage generators, the multiple generators with just the LRG off the bus and the HRG on the generator, you may not need these things. You actually don't need to have a vacuum switch for that example. I want to go over the different ones, but I'm generally speaking about the single generator application with this. Once again, you can use that in a multiple generator application, but you don't have to. So here's an example of a generator that's using different components. One of which is a vacuum switch. This is what isolates that LRG. You're going to have a high-speed disconnect essentially. You're going to want to match your generator, your main switch. So you're basically going to want to coordinate with your generator, usually at less than 7 cycles. So it's going to have to be fairly quickly to operate completely within that time frame. Just as a note, what I've seen so far in my research, a lot of times you have control power 120 volts for these medium voltage vacuum switches. So you're going to have to figure out a way to provide that. If you have turbines, don't assume that they're exactly the same as a generator, because we might have to coordinate them a little differently. So I just want to make a note. We're not going to go into details on that, but I just don't necessarily, you probably want to do it more sequentially than you would with a generator. So the second one is lightning arresters. So it's kind of a domino effect of sorts, right? You need a fast speed switch. You're switching over from a higher current to much lower current, and you're going to create transient voltages because of that. What you want to do is you want to use a lightning arrestor or some surge suppression device essentially to control that from protecting against the installation of your generator essentially. So because of this, we have to use this. So it's an example of a medium voltage arrestor. It's just switching voltage essentially, but you want to install at the Y point, just like that picture I just showed you indicated. You want to install at the Y point so that generator installation is not compromised. Another thing to consider is harmonic filtering. You're typically going to want to have, it doesn't actually matter where you have this. What you're doing here is you're trying to, have accurate information for your relays, for your controls. So if you have third harmonics, which typically the third harmonic voltage is present, you can create some with the generator. Essentially, you're going to need to have some kind of a filter here, whether it be a high pass filter or whatever it's going to be. You're going to need some kind of a filter to be able to get rid of those third harmonic voltages, so you're tripping or you're alarming properly. So it doesn't matter. Once again, it doesn't matter if it's if you're just ignoring the third harmonics or you're actually actively filtering it out. Just you need to make sure that there is some way you're doing it. It also doesn't necessarily matter where you do it. You have to do it. As long as you're protecting the controls relays, you can do it separately in the HRG. You can do it on the relay, wherever you can get it from, as long as that relay is not tripping or alarming based off of that third harmonic false current essentially, because false voltage, because the voltage is going to be fundamental from the system. So then we come to the resistor. What does that look like? This is the so for the low resistance ground, it's very similar to a standard. I've already shown you an example of it, but basically it's going to be, you're going to size it. If you're a single resistor, you're going to have, it's usually going to be like a 200 amp let through current, or potentially 400. Keep in mind that if you have multiple parallel generators, that you're going to want to keep that total current down. You may have your own idea. I would say 1500 amps. Some people say 1000, depending on what your goals are. But try to keep it down as much as you can if you have parallel LRGs. But the point is you're going to be using a 10-second, 200 or 400 amp typically resistor. And that's the low resistance ground. Now, the high resistance ground, I show here, as I show right here, this is going to be more likely to be usually 10 amps. It doesn't have to be 10 amps. It can be 5 to 10 amps, but usually most of the time we see 10, just because it just makes it easier that way in terms of capacitive charge current. It's likely that it'll be a little much less than that, but it kind of takes that out of the consideration. Usually you want a longer rated resistor. Doesn't mean you have to have one, but just keep this in mind. You're going to want to have this resistor rated for the entirety of the wind down of the resistor. So you want to make sure that the entire thing is completely shut down and stops before your resistor gets to its max temperature, essentially. So I would recommend 30 seconds just based off of that, because your wind downs can be long. But if you have a scenario where your wind down only takes 3 seconds, you understand the idea. You just need to make sure that it's long enough that it addresses the wind down. Resistor only is needed. Like I see a lot of people looking to try to use like an HRG system, like a pulsar system, with their hybrid resistance ground system. You don't actually need all that stuff. Really, you because of all the relaying you have, you really just need the resistor. You may need a current transformer to accommodate the 51G inside the resistor itself, but more likely in this scenario, especially with the scenario that I showed you before, you probably would have that at the differential. You probably use that in coincidence with the differential relay, which you already need CTs for. So others, make sure you can get. So based on this, it has to do with your personnel. You want to make sure your technician or whoever's operating the generator understands that when you have a stator fault, you're damaging your generator, essentially. That's the definition of a stator fault, essentially. So the longer you operate that generator, the more damage you're going to have. So a lot of times, a technician, if they had an issue, they realized that the generator was stopped, maybe they would try to reset it, restart it. That's not something you want to happen in this scenario. So if you have a differential relay, you may want to lock it out. There may have some training or whatever it's going to be. You need to make sure that there's a way that that technician knows that he's not to try to restart this. So now we're going to move on to poll question number 2. Stu will generate that for us, and we'll move forward here in a few seconds.
So we went from 75% roughly never having designed or implemented a system to now, thanks to your knowledge that you've imparted, over 80% have said they would consider it in the future.
I believe everything you just said besides that first part, but I appreciate it. All right, so let's move on. So let's go talk about applications. All right, I've already mentioned that I'm medium voltage only. So I know it's a subset of what a lot of engineers are typically used to dealing with. So it's obviously it's a little bit of a niche application, I understand. And so you know, the engineering reasons to use this kind of push the application. So let's say your generator operation is critical, right? You have critical infrastructure, you have cogen. What happens if you have a stator fault? Okay, you have downtime, which is not acceptable. Now you may have stuff built in. Now, if you have if you have 2 generators, if you have complete redundancy, whatever you just have to consider that, right? But if you don't have all that stuff, or if you don't have enough of it that you feel, you might want to use this for the added protection, so you don't have to. You're going to be much less downtime. You're not going to have 0 downtime, because if you get a stator fault, you're going to have downtime, but you're going to drastically reduce the downtime you potentially could have. Expensive generators. We're basically talking about insurance, right? We're increasing the amount of resistors we use for protection, specifically for faults internal to the generator. We're not really protecting it against that. We're not protecting it against that at all if you have solid ground system. We're protecting it against that a little bit, but not nearly enough, in my opinion, if you have a low resistance ground system. So the more expensive your generator, the more it's like basically like buying insurance. You're going to buy a little bit more money on the front end, but you're going to protect yourself on the back end. So that's kind of how it works. Usually, you're going to be more likely to use this if the more expensive the generator is. You're not going to spend an extra $15,000 on something that is like only $30,000 or something. You understand what I'm saying? Because to be honest, if you have a new generator, this is not. I don't have any data to support the fact that it's not likely, but just common knowledge. Typically, you're going to have these types of faults, when you have insulation breakdown, stuff like that, that usually happens with older generators. It's much more likely for it to happen with older generators. Okay, that kind of brings the point down here. Complete protection is important. If you, for example, you're an engineer and you didn't realize that, look, I'm good on all my faults. I have a system fault. I'm low resistance ground protected. I'm good to go. But I didn't realize I didn't have this protection when it comes to stator faults. It's not likely, but I don't like the idea that we're not protected. So that's kind of another option. Older generators, like I said, usually, you know, you're going to be much more likely to see this on older generators. As part of a strategy, you could elongate a rewind maintenance schedule. So what does that mean? Like instead of rewinding, just like let's say every 10 years, 15 years, based off of you know, insulation breakdown, et cetera, you could do some kind of additional testing to kind of show you what your insulation looks like. And because you know you have that extra protection there, you could elongate that maintenance schedule. It's happened before. There's papers on that strategy being implemented, so I just wanted to share that as well. So those are some of the reasons why you could use hybrid high resistance ground. So this is a general number. I just want to kind of do a very brief economic analysis of what it could look like for your HRG solution. Now, if you have a single generator solution, we're looking at roughly $25,000. It could be a little more depending on your options. It could be, if you have a zigzag, you know, all these things. It could drastically increase the price. But generally speaking, if you just have kind of what I showed you, we're roughly looking at this. You know, so it's about $15,000 to $70,000 more than your average low resistance ground for that same voltage. Let's assume a 15 kV solution. Your average 15 kV generator repair is about $50,000. Now, I will say this: I did not find any published data on this. I didn't see any studies that could tell me what this. So what I did was I went to a generator repair facility and I asked them to look at their history and tell me what they. So this is obviously a small subset. So if somebody's out there like, oh, this isn't right. It's much less. It's much more. I'm guessing it might even be more, but if you have different knowledge, just understand that this is trying to give you a guideline. But the more data you have, the more knowledge you have, the better off you'll be. But the point is that you're going to have a good amount of repair costs. And if you have just a low resistance ground system, it's going to be much more extensive based on what I just told you before. So this number easily, I'm very confident this number would eclipse this number. Is what I'm trying to say. If you have a turnaround for a rewind, it could be 6 weeks, etc. If it's extensive, it could be longer than that. Obviously, replacements could be, if it's not in stock, could be a lot worse. So these are the kind of alternatives you're looking at. These are the kind of insurance terms you're looking at. Speaking of insurance terms, I didn't put this down as a bullet point, but it's very important. You know, one thing that's actually driving, that has driven, you know, even high resistance ground or low resistance ground. But one thing that's driven it in the past, not just engineering, not just their knowledge of the topic, but also insurance companies. If you're looking to do a retrofit, you know, or if you're looking to do a new build, either way, what is the insurance impact? And this could be an end user question, but if you're an engineer, you also could be like, look, you might want to check with your insurance company if you're doing a cost benefit analysis. This might be a good way to go. You're going to have added protection. A lot, to be honest, insurance companies have been driving some of this stuff, so just keep that in mind. Okay, so in conclusion of our, I would call it an introduction to hybrid high resistance ground, essentially it's a viable solution for medium voltage generators for protection against, you know, basically generator faults. It definitely is more complicated. You have more relaying. You have there is more the settings of the relays are. I'm not a relay expert, but you know I've read a lot of papers. It's more complicated than your standard low resistance ground system. No question about it. However, it is doable, and it gives you that protection you need for the generator. And once again, if you go through the applications, you kind of try to figure out what your cost would be if that were to happen. Or let's say your generator is old, you're looking for a retrofit because your generator is 20 years old. Whatever the situation is, you guys are smart enough to do the cost benefit analysis. I just kind of want to give you the tools to start that analysis. So in terms of any questions, you guys will receive an email with a link to the, actually, let's see. If you want, that's actually true, but if you don't get the video, I think it's tied to your email, but sometimes it only goes to the people who didn't show up. If you didn't get a video, you will get a link. You will definitely get a certificate of participation. And one thing I want to note about that is usually a certificate of participation is due to or is needed for a PE, continuing education, et cetera, essentially. So every single state has different requirements based on that. If you get your certificate and you don't feel like it meets the requirements of your state, just let us know. We'll modify it. But for most people, this will be sufficient. And if you want a PDF version, please let us know. Email us. We'll get one to you. And that's it. So here's the references. If you guys want to look at that, that I used for this. Just keep in mind that there's 4 papers here, so it's actually a little more than 3 papers. But the point is that there's some references. We're going to go to question answer at this point. Stu, let me know what we got.
One of your very early slides, John wanted to know what is meant by faulted circuit must be segregated.
Basically, all it means is if you have a low resistance ground system, or even a hybrid system ground system, you're going to be tripping. It just means that you're going to have to open a breaker, and a lot of times it's going to be your whole system, so it's just going to be shut down, right? But sometimes it's going to be segregation. Tripping is all I'm saying. So you're going to have to trip on a low resistance ground system. Whereas on a high resistance ground system, not necessarily. You're going to be continue to operate on a lot of different applications. You're going to be continue to operate with faults.
Stephen in Indiana said, I have seen 60-second rated resistors for the 10 amp high resistance grounding. Is a 30-second rating okay, or is it safer to stay with 60 seconds?
It really just depends. If you don't feel like 30 seconds is enough time for your system to completely shut down, and that includes literally your entire generator coming to a complete stop, then please don't do it. Yeah, please use what you need to use. That some people are comfortable with continuous. We used to just recommend continuous. I don't actually care. The only reason I bring it up is there's a lot of people, or at least there's a handful of people that have presented the idea that they're specifying 10-second resistors for this application. That may work, but I get a little bit nervous when you say 10 seconds. So make sure it's long enough for your system to completely shut down, which includes the movement of the generator.
Tim in Virginia, why don't we see this application more often? Are customers just willing to take risks on stator faults?
My personal opinion, there's 2 reasons. Number one, stator faults aren't that common in new equipment. They're not, to be fair. They happen, but usually it's related to insulation breakdown, which happens with time. Number 2 is just knowledge. I would say there's a percentage of the engineering community that knows about high resistance grounding. There's a percentage of that, probably not a large percentage of that group that knows about hybrid grounding. So it's kind of it's from my perspective, it's the same idea. For the last 12 years, I've been trying to educate people on high resistance ground, and usually the idea kind of sells itself, to be honest with you. And that's so people are using it more and more and more. It's the same with this. Now with this one though, however, there is a cost. I think it's more. In my personal opinion, high resistance ground is like a no-brainer to some degree. But hybrid grounding is basically application specific, and you really should do a cost benefit analysis. If you feel comfortable with it being fully protected and not taking a chance on a small, if you have a new generator, let's say on a stator fault, then I would say yes, go for it. But you have to look at the cost and you have to look at the benefit of it. So that's where I think there's a little more cost benefit analysis in this application.
And I think the last question we'll get to, because I know we're bumping up against the time frame probably most people allotted. Felipe was wondering, is there another method or solution to protect the generators in these situations?
I have not found a full solution. Now you could talk about, there are some generator manufacturers, and I'm not saying they're wrong at all. I don't, but from what I've seen is that there is some protection that you can stop. You can basically force stop the generator, and there's different ways that protect it more, but you're not going to be eliminating all the damage. If you want a more full solution, I would go with, or maybe even in addition to those things. I don't want to mention a generator manufacturer, but there's at least one out there that talks about how, well, look, we can detect it with this, and we can kind of force stop our generator. That's fine, but that's not going to get rid of all the damage. So I would recommend either using that and this, or but it just depends. Like I said, as long as you understand what it does and the fact that it doesn't completely protect your system, then it becomes another cost benefit analysis. But there are some generators that offer some protection, but not full protection. All right, guys, I think that's going to be it. I appreciate you guys attending. If we didn't get to your question, we'll go ahead and email you. Otherwise, feel free to email us, and we'll get back to any questions you guys may have. Appreciate it. Next month, we're going to be going over some new IEEE regulations. That's going to be the topic of our next discussion. So if you're interested in that, sign up. We'll be sending out a reminder to you guys, but that's what next month's topic is going to be. So take care, guys. Until next time, appreciate it.